Hello everybody, how's it going today? My name is Connor, welcome back to another video. Welcome to Raug. Now, some of you may or may not know that I'm an experienced electronic musician. I've been working on electronic music for about, I guess, 16 years at this point. I'm 28 years old, I've been doing it since I was 12, so that checks out. Um, and I've always had an eye out for ways to combine my music love and my programming love. But I wasn't satisfied with any of the current options that were available to do kind of music and programming at the same time, which was, there's things like Pure Data and Max/MSP, but those are visual programming languages that are kind of not my preference. I don't like working with, dragging nodes to graphs and connections and wires and stuff like that. That's not what I prefer to work with. I prefer to work with code. So then you might say, well, what about Super Collider or SonicPy? Or something like that. And well, those have a weird syntax, in my opinion. It's kind of a weird thing where you got like a special domain-specific language for these audio programming languages that are kind of already made, that are kind of made for live coding, and so I didn't want to do anything like that. And then you might say, well, why don't you use Juice? Well, Juice, it uses C++, and obviously I'm a Rustacean, so that's not going to fly for me. So I wanted something that I could use with a regular programming language, so probably something like Rust or Python, and something that made sense in my brain. So, because I didn't really get Pure Data or Max MSP, I didn't get Super Collider, I didn't get SonicPy. None of those really made sense to me. It made sense to my brain, the way my brain works. My brain has a very particular way of doing things. So, I wanted to kind of just make my own way, you know? I wanted to make my own way of doing music programming and audio programming. So that's where we are today. And what you just heard is the results of what I've been working on so far. So what is this? Well, I'm calling it Raug. RAUG. It stands for Rusty Audio Graphs. And essentially it allows for the construction of single flow graphs and the ability to pass signals through them. So it allows you to do things like this example of how to use it. Kind of a complicated example, but you get that point, right? So you can set up a graph. You can add outputs to the graph. You can add things like parameters and nodes to control the signals throughout the graph. And then you can do things like, oops, there we go. Just add processors to this graph, and the processors will take their inputs from other nodes in the graph and then produce their own outputs that are then stored inside the runtime, which we'll get to that in a bit. So basically, in layman's terms, I can make my own instruments and audio effects, virtual instruments, virtual audio effects, using this little system that I've created. And this whole thing was inspired by many of the aforementioned existing music programming things that I mentioned, especially Max. It's kind of has a similar structure, similar kind of way you use it to Max, except obviously this is in code and Max is visual. So, because I did really like, I did really like what Max did essentially. I just wanted a different way of interfacing with it. So this is what I'm doing now. So you might also remember that I've made something like this before. It was called Paper, PAPR. But the thing with Paper is that it was really kind of hacky. It was really kind of slow. It wasn't very efficient. It wasn't very easy to use for people other than me. So it had its own specific domain-specific language, kind of similar to Super Collider or SonicPy, where you just had to learn a whole new programming language in order to even use it, and it was just a big old mess and too complicated than it needed to be. So, but this new version is way easier to use, and much more. It's much more lightweight as well, and it's just way easier to use and makes more sense. So some of the design goals that and actually let me pull up the actual repository here. Like I said, Raug is a library for writing and running digital audio processors and signal flow graphs in Rust. Now, design goals for this are the following. I want it to be fast. I want it to be lightweight. I want it to use easily copyable types. Types that are cheap to copy and use references as much as I can. I want to minimize the amount of heap allocations that I'm doing. Obviously, I can't use stack memory for everything, but I want to especially make sure I don't allocate on the real-time audio thread. So going over basically how this works, how I've kind of set this up is I have two main API levels for Raug. The first is the lower level API, and that is the processor API for writing high-performance raw audio processors. So these are the things that actually do your DSP math in Raug, and you have to write these in Rust. And then I have the builder API, which is easily bindable to other languages, and in fact, I've already bound it to Python. And the builder API is what you were seeing before in the example, where you're able to construct these audio graphs. It also includes a runtime that uses a CPAL graph crate under the hood for running these serial graphs in real time, or you can just render them to a file. And also, I made a point to exclusively use 64-bit floats internally in Raug. There's no way to turn it into 32-bit floats. I just, for my purposes, I want quality as much as I can. I also have a relatively fast computer, so 64-bit is the way to go for me. So potentially in the future, I might end up making these 32-bit floats as an option, like a cargo feature or something. But anyway, so let's take a look at these examples that I've created and kind of go into them in more detail. So, all right, so first I'm going to go over the Rust examples, and then I'll go over the Python examples. So another thing too is that Raug is my first Rust project that's been fully documented. It's got all the documentation. I can actually pull it up. Cargo doc open, and you can see that it has a README here, and then all of these modules are fully documented with doc comments. So all the functions are documented, all of the other stuff is documented. And it does the same with the examples. I've written comments in the examples so that you know what's going on. So you can see here I'm initializing logging. This is just to get some log messages in case I get any errors. Creating a graph, a graph builder more accurately. I add some outputs to the graph, and then these add-output functions, they return a node. And these nodes in the graph have their own have their own methods and parameters that allow you to do things with that node. So like out1 dot blah blah blah, and then you can do all kinds of stuff with these nodes, and it will automatically connect the appropriate processors and nodes and connections in the same graph that node was built with. So, and then add a sine oscillator. So it's, again, pretty simple, pretty self-explanatory. Make a sine node, graph, add, sine oscillator, new, 440 hertz. It's pretty intuitive, And then I've also added the operator overloads for the nodes, so that you can do things like just basic math on them, and this will automatically hook up a multiply processor to the appropriate inputs and outputs and return that processor as a return to node. So now for nodes with multiple inputs and outputs, you can actually use the .output and .input API on the nodes, and you can select an output at a certain index. You can also actually use a string here, and it'll work just fine as well. It takes a trait that allows Raug to dynamically kind of infer what kind of output, what output you mean, based on the processor's specification. So you see the sine oscillator here. I've written documentation for this as well, where it has a table of the default inputs and outputs that this thing has, and their names, their indices, what kind of signals they are, etc. So it's all very well documented. And then once we got our sine oscillator connected to the outputs of the graph, we can build a runtime using the graph, and then run that runtime in real time for 1 second using default backend, default device. And then if we run this example, cargo run, let's run it in release mode. This should be beep. And there we go, there's our beep. So as you can see, the API itself is pretty easy, intuitive to use. Another thing that you can do with this is you don't have to only work with audio. So I want to go into this example, bang.rs. So this is where the max influence starts to come in, and the max and pure data kind of influence starts to come in. So you don't actually have to only pass audio through these nodes. You can also pass what's called messages. And messages can be of a few different types, one of which is called a bang. And the bang is basically just like an activation message. It's like, do that thing that you do. Whoever node is receiving that bang, the bang will indicate this is like an activation of that node, right? Whatever that means for that particular node. So here we can add a metronome with a period of 0.5 seconds. This means that it will tick every 0.5 seconds. You can easily convert like BPM to this or whatever, yeah. And then I'm doing the same thing. I'm adding a sine oscillator with frequency of 1, doing a weird thing where I'm like, this is where I'm just kind of just testing the message system to see if I can send a message to a print node. The print node is good for debugging, where you can just print a message into the console based on whenever you receive a bang. So this should work as well. Yep. Now it's kind of randomly, not randomly, but like at a certain rate, outputting the frequency of the oscillator that is being modulated. And then we have the Param example, which allows you to kind of control parameters within the graph at runtime. And you need to use a special type of node for this called a param. And you can actually convert inputs of nodes into params pretty easily just by doing the dot input and then get an input name or index, and then do dot param and give that a parameter name with the initial value optionally. And then this will allow you to, like I said, control the graph while it's already running. So normally you can't modify the graph while it's already running, while it's being run via a runtime, but with params, you can just kind of hold on to those params and it'll automatically sync up with whatever's inside the graph that's listening to that param. So if I do the param example, you should hear a few different tones here. And there you go. So we're setting the frequency of this param in real time as the graph is already running. See? So that's the params. And then to kind of show off the processor API a little bit, this is how you would make a custom processor, a custom DSP processor in Rust using my Raug library. So first you gotta define your state for the processor. And this is what you're actually going to be passing into graph.add. So I think you got to implement my process trait for it. And processors, this part of being a processor, you're required to implement debug and clone, just for purposes of debugging and being able to copy the graph, clone the graph itself. But it shouldn't be any issue for most processors. You can just derive those. The goal is to keep the state of the processor pretty simple, make it pretty easily copyable, pretty easily debuggable. And then you implement this trait. And the process trait has a few different properties to it, a few different methods that you have to implement. The first of which is input spec and output spec. So these basically just tell the graph what types of inputs and outputs you are expecting to receive and output for this processor. So you return a vec of signal spec, and the signal spec is just information about the input or output. So you can give it a name, you can give it a minimum value, you can give it a maximum value, and you can give it a default value. So in this case, for the scaling processor, I simply have one value, or one input, which is the input signal, and then one output, which is output signal. And I could actually theoretically add another signal input here for the gain, and then I could set the gain appropriately, but I'm just keeping a simple, really simple example. It's just a constant gain for now. Then the only other required method to implement is process itself. So this has changed recently with my with the development of this project. And actually, it just changed yesterday, last night actually. So the inputs to this process function are this process inputs struct, and as you can see in the process inputs here, it is all borrowed stuff. So this makes the inputs really, really easy and fast to copy over into this method, to pass into this method. And then the outputs are also borrowed. They're mutably borrowed. And these just allow for just a really easy, really fast calling of these methods. So really efficient, really cache efficient. So, and then the process method, you can iterate over these process inputs and process outputs You can get the input at a certain index and output at a certain index, and then loop over these. I like to use iter tools for this. The izip macro is really useful, but you can just use a regular iterator or just wherever you want, zip them manually, iterate over the index, whatever you want to do. And then you do your processing for each sample and the buffers. So, and then you can just add this to the graph like a normal processor. So you can see graph.add sine oscillator, graph.add gain proc, gain with the set gain. So I want to also go over the Python bindings to this library, just real quick. I'm gonna go over, see what's an example? Pygame Theremin, there we go. So one of the cool things about having Python bindings to this library is that I can integrate it with the rest of the Python ecosystem. So I can use something like Pygame to create something like an interactive Theremin. So if I go over to Python and then Python examples, Pygame Theremin, this should work. There we go. Create an interactive little musical instrument using Pygame. So, or you can do anything you want with anything else in the Python ecosystem. You could use pandas to load some parameters into a synthesizer, or you could use, TensorFlow or PyTorch to create an AI that generates these little signal graphs. Its possibilities are really endless. So that's really cool. Another benefit of having a Python API for this is that you can, if you're like playing around with like different synthesizers and you want to mess around with different graphs and stuff, it allows you to really easily and rapidly prototype those. And instead of writing them in Rust, you can just write them in Python. The Builder API allows for that to be really easily translated. So what is to be expected in the future for this project? Well, first of all, I would definitely want to add some more built-in processors. Right now I have a few different modules for the processors. I have like things like dynamics, like limiters. I want to add a compressor eventually. I don't actually have a compressor yet. I have filters, including a biquad filter and a Moog ladder filter, low-pass filter. I have lots of math processors that are just various mathematical stuff. I have some oscillators, including a sine oscillator, a phase accumulator for building other oscillators. I have a saw oscillator, which is not anti-aliased. I have a band-limited saw oscillator, which is anti-aliased and band-limited. And I also have a band-limited square wave oscillator or pulse wave oscillator. So I have various storage-related processors like audio buffers, buffer players, buffer readers, and also registers for holding a single message and just kind of weirdly outputting it. Time-related stuff. I've got delays. I've got metronomes, and a bunch of other stuff. Really cool, but I would like to add more. I want to add more built in so we can actually get some cool synthesizers and cool effects being made with this thing. Other thing that I want to do with this, and this is something that I've already kind of started the process of, is doing GUI integration. So I can actually go to Raug Iced here. I'm using Iced, which is a Rust GUI crate. I can do cargo run demo, and this should bring up a little graphical interface where I can actually control the sine wave with a knob. Yeah, so I can start the audio. Oh, sorry, that's loud. But you get that point, right? Where I can control this pitch of the sine wave using this knob. So that's pretty cool. This is very incomplete right now, but I do want to work on that some more very soon in the future. And then eventually it'd be nice to have some kind of live coding thing, especially for the Python API, where I can have like this environment where I have the server running that listens to the graph changes, and this allows me to hot reload the graph and hot reload parts of the graph in real time. That'd be really cool, but that's probably a far off thing for the future. So other than that about does it. Thank you all very much for watching. If you liked the video, please leave a like. If you want to see more of what I'm doing with this when my other projects are running in Rust, please subscribe. And other than that, I'll see you next time. Peace out.